right, let's talk about section 1.6. This is all about set operations and compound inequalities. The first thing we're going to do, though, is have kind of a brief introduction to set theory. So, friendly reminder that a set is a collection of objects. So I could have the set of the letters A, B, C. I could have the set of countries in Asia, and if we wanted to, we could list out all the elements in this set, right? So we can define a set by either describing what it contains or listing all the elements. Now, what's nice about these two sets is they are finite. Now, what does that mean? Finite means that I can count the number of elements in them. I can also have sets that are infinite. An infinite set could be x such that x is an integer, right? The integers are all the negative numbers, all the positive numbers, and 0. So I could write it out by describing it, or I could write it out by listing a few of the elements with ellipses that let me know the set just kind of goes on and on forever in both directions. So these are examples of sets, and I would say A is an element of this set, -2 is an element of this set, China is an element of this set, right? We can have either finite or infinite sets. So given any two sets, I can find their intersection. So the intersection of two sets, A and B, we've written A, this upside down U means intersect B, and what it is, it's all elements in both A and B. So let's let U be our universal set, which contains 1, 3, 5, 7, 9, 11, 13. A contains 1, 3, 5, 7, 9, 11. B, 3, 7, 9, and so on and so forth. I just wrote on this too much. If I wanted to find A intersect C, what I'm looking for is the elements that A have in common and C have in common. So A has a 3, C has a 3, A has a 9, C has a 9, but A doesn't have a 13 and 13 is not an A, so their intersection is just 3 and 9. If I look at B and D, B has 3, 7, 9, D has 1, 13, they have no elements in common. We call this symbol, that means they have no elements in common, the empty set or the null set. That just means that they have nothing in common. And if I take B, which is 3, 7, 9, intersected with U, which has everything, 1, 3, 7, 9, 11, and 13, we're just going to get B back out. Also, it's a friendly reminder that we would call B and D disjoint sets because they have nothing in common. So this upside down U represents the intersection, and then I'm only looking for elements contained in those two intersected sets. Union is quite a bit different. Union's represented with this U, right? And it says, given any two sets, I only want the collection of all elements in A or all elements in B. So if they're in A or B, we just write them once. Let's look at A union D. So the first thing I'm going to do is I'm going to take all the elements of A. I've got 1, 3, 5, 7, 9, 11. And then I'm going to collect all of my elements in D that I don't already have. So I already have a 1, I already have a 9, but I don't have a 13, so I can add that to my set. So here's the set A union D. Next I look at B union C. B contains the elements 1, 3, 7, 9. Separate them with commas, otherwise it would look like 1,379, just a friendly tip. And C equals 3, 9, 11. So I already have a 3, a 9, I need that 11. So here's B union C. If I have D union my universal set, I'm just going to get back out 1, 3, 5, 7, 9, 11, 13. That's everything in U and also in D, which is still just the universal set. So when I have two inequalities and I say I want x plus 1 to be less than or equal to 9 and x minus 2 to be greater than or equal to 3, and means both, and means intersection, that it has to be true for both of these. So where we find the intersection is going to be where our two graphs overlap. So I'm going to go ahead and solve this, and then I will graph them in different colors. So I'm going to subtract 1 from both sides. I get a is less than or equal to 8. Here I add 2 to both sides. I get x is greater than or equal to 5. So I need x to be less than or equal to 8 and x to be greater than or equal to 5. Let me go ahead and graph x is less than 8. So I'll write on my number line. I'll have 5, 6, 7, 8, 9, 4. How's that? So back to orange. If I have less than or equal to 8, that means 8 is included. 8's an endpoint. And I say that x is less than or equal to 8. So that can be everything to the left. Next, if I graph x is greater than or equal to 5, I know 5 is included in my solution set. And then I graph everything where x is greater than 5, which would be like 6 and 7. So I'm going to shade to the right. Now, I'm only looking where these two intersect, where they overlap, right? Where they overlap is between 5 and 8. So this would be the solution to our given set of inequalities. Next, let's say I have x plus 2 is less than 5 and x minus 10 is greater than 2. I'm going to go ahead and solve both these linear equations separately like I would have before. Then I'm going to go ahead and label my number line. I need to have the numbers between 3 and 12. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, it just fits. I'm going to go ahead and graph x is less than 3. 3 is not included in my solution, and my graph is x is less than 3. Next, I'm going to go ahead and graph x is greater than 12. 12 is not included, and x is greater than 12 will be everything over here. Where does this intersect? Where did I have both blue and orange? The trick is that I don't. They don't intersect anywhere. So this is going to be the empty set because they have no intersection. Next, I think this might be our last intersection. If I have negative 3x is greater than 7 and 5x is less than or equal to negative 20, I'm going to go ahead and solve both these equations. I'm going to divide by negative 3. I get x is less than negative 7/3. I'm going to go ahead and divide both sides by 5. I have x is greater than or equal to, less than or equal to, because I didn't divide by a negative. I'm so tricky. X is less than 5, which is negative 20 divided by 5, which is negative 4. So let's go ahead and graph both of these, and I'm trying to find the intersection. So I'm going to graph x is less than negative 7/3 in blue. Let me go ahead and label my number line. Negative 7/3, that's close to negative 3, right? So negative 4, negative 3, negative 2. Oh, let me move things over so we can see things a little more clearly. Negative 5, negative 6, negative 4, negative 3, negative 2, negative 1, 0. Okay. So if I have x is less than negative 7/3, negative 7/3 is just a little bit more than negative 2. It's not included, so I'm going to leave an open dot, and I say x is less than negative 7/3. Then I can highlight everything to the left. Now in green, I'm going to go ahead and graph x is less than or equal to negative 4. Negative 4 is included. And I'm going to highlight everything where x is less than negative 4, which is to the left. So my intersection is where these two graphs overlap, which is going to be from negative infinity all the way to 4, the square bracket, because 4 is included in my solution set. Next, we're going to talk about inequalities with or. Or means union. It can be in one or the other. So let's go ahead and see what the graphs of those look like. If I have negative 4 is less than 4x, I'm going to go ahead and solve for x. Negative 1 is less than x. Divide both sides by negative 3 on the right. I get x is less than or equal to, greater than or equal to, because we got to flip the sign, greater than or equal to negative 3. I'm going to go ahead and graph both of these. So let's go ahead and label our number line. I've got negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3. In blue, I'm going to plot negative 1 is less than x. So let's go to negative 1, which is not part of my solution. It's not an endpoint. I have negative 1 is less than x. So that means x is greater than negative 1. Let's check. If I pick 0, negative 1 is less than 0. That's true, so I'm going to be shading to the right. All right, if I have x is greater than or equal to negative 3, let's plot that in orange. Negative 3 is included, and x is greater than or equal to negative 3. That's going to be shading to the right. So now I'm looking for the union. Before, when I was looking for the intersection, I was looking where I would be looking for where the blue and the orange overlap. Now I'm looking for anywhere the blue and the orange touches. So I would have from negative 3 all the way to positive infinity. That would be the union, also done with this symbol, of these two sets. For our next example, I've got negative 4x is greater than or equal to 8, or 5x is less than or equal to negative 15. Divide both sides by negative 4. That gives me x is less than or equal to negative 2. Divide both sides by 5. I have x is greater than or equal to negative 3. So let's go ahead and plot this. Remember, this is union. I'm going to label my number line. Negative 4, negative 3, negative 2. If I go ahead and plot in blue, x is less than or equal to negative 2. I'm going to go to negative 2 and know that that's an endpoint. Now I have x is less than or equal to negative 2. So I'm going to shade to the left. Next, in green, I'm going to plot x is greater than or equal to negative 3. Negative 3 is an endpoint, and x is greater than negative 3, so I'm going to shade to the right. And I'm looking for the union. So I'm looking for everything that is either blue or green. Well, that covers the entire number line, right? So my solution's from negative infinity to positive infinity, or we could write all real numbers. Next, I have negative 2x is less than 6, or 4x is greater than or equal to negative 20. So I'm going to go ahead and divide both sides by negative 2. I get x is greater than, because I have to flip the sign, negative 3. Divide both sides by 4. I get x is greater than or equal to negative 5. So let's go ahead and plot this. I have x is greater than negative 3. So I'm going to have, let's go ahead, negative 4, negative 5, negative 3. So x is greater than negative 3. Negative 3 is not included. We're going to go ahead and graph that in blue. And for x to be greater than negative 3, I'm going to shade to the right. Next, I have x is greater than or equal to negative 5. Oops. Let's change colors. So I have negative 5 over here. It's included. X is greater than negative 5. So my solution set goes from negative 5 all the way to infinity. That's how we're going to work with union.